Hey, good morning, guys. How are you?
Yeah, good morning, Shrikant.
All right. So, any questions on PCA? What we discussed yesterday?
Uh, I mean, the concept is okay. Only thing is I'm
Mhm.
not very much aware, still aware of the multiplication, how you do it. Uh, like in one slide, you've done that lambda plus two, lambda plus two. How did you do that? I mean, I haven't done it for a long time, so just wanted to know how was it done?
Okay. So,
Yeah,
see,
this one.
this is your equation, right? A
Yeah,
minus
yeah, yeah.
lambda I.
This one
So,
I got it.
yeah, if you solve this, you will get
Yeah.
this kind.
How do we get from this to
Yeah, so
lambda plus
this 2 minus lambda into minus 6 minus lambda into 4 minus 4. So that is a matrix multiplication, if you remember. So it will give you a quadratic equation. That quadratic equation, you have to, when you solve it, you will get in this form. So one step is missing here. That step you can see that in the Word document which I have shared. Have you gone through that Word document?
Yeah, I was going through that, so I was little confused over there also.
Okay.
So I thought because there is a correlation matrix you have created and all, so I
See,
just
if
want
you
to.
can see my Word document.
Yeah, this is
Yeah,
fine. So
this is fine.
from this step
Yeah,
to next step, how do we go
right.
that?
So you multiply this minus this. Okay, so you will get this equation.
So you're saying multiply the diagonal elements
Yeah.
and then minus the multiplication of the
If you right,
other diagonal.
if you multiply this 0.616556 minus lambda into this, you will get till this part 0.44180 till this lambda square. Then minus of this. If you
Minus of multiplication again of these two.
multiplication, yeah, multiplication of these two values, you will get 0.37877. So if you solve
Okay.
this, okay,
That
then you
then
will
I know.
get this. If you solve this, then you will get lambda minus 1.28403 into lambda minus 0.049084. So these are the two values which you can consider for lambda 1 and lambda. So basically, all these are like matrices, multiplication, and all those things, and the linear algebra, which is being used here. But however, see, this don't waste time in you can learn this slowly. It should not be a should be a showstopper. Okay, so you have to first understand the whole concept and see that. And in when you are doing with Python, you don't require all these calculations, and you can just use the package, and it will give you all these values for further use. So emphasis more on the concept and the application of that concept in solving, and how you can use this concept by using Python. And later, based on your interest, you can deep dive and you can go detail into mathematics, calculations, and everything for your understanding, for your better understanding. But
Okay.
for now, don't spend a lot of time on this mathematics, because in real scenario, it is not used. It's just for your understanding how the things are working internally. For that, you need to understand all this mathematics. Got it?
Yeah.
Okay. Okay, so today what we are going to do is we will see that how can we use this PCA, okay, and what kind of problems can be solved through PCA. Okay, so we will take this particular use case, and this use case is a pretty different use case. This is for this is this use case is related to beverages industry. Okay, it is related to wine testing and all those things. So here there are different kinds of wines. So we have around 178 different wines. Okay, and the composition of those wines. So what is the alcohol content, malic acid content, and all those things. Okay, in each of the wines. Now, based on the attributes of these wines, they have kind of and the customers who are buying those wines, they have segmented the customers. So which kind of customers are liking which kind of wines? Okay, so they kind of segmented that. So you will find that there are three customer segments. So what they have done is they have kind of categorized all these wines based on the attributes and based on the customer who have liked those wines. They have categorized into three groups. Now we have to go and train the model, a classification model on top of this data, which can predict if there is any new wine coming and if there is a wine testing happening. So based on the attributes of that wine, we can target that particular wine to the appropriate customer segments. Okay. So this is the use case. Now you are seeing that this particular data science has no limits. You can use it anywhere, okay, in any domain, in any industry, if the data is available. All right. So, but what kind of major challenges you may face when we are talking about this particular data? It is all about basically we are talking about the composition of a particular wine, right? So definitely, uh, if there is a high what do you say concentration of any particular uh, component, and definitely it would impact the other component. If, let's suppose, I'm just assuming, I'm not a domain expert here, but I'm assuming that if there is a high alcohol content, so definitely there could be a chance that malic acid would be also high, or because of the malic acid, the alcohol content could be high. Okay, the color intensity may be high, right? If the alcohol is high, so generally we see the color intensity will also increase, right? If it is mild or if it is light, the intensity is low. So in this particular data, there could be a high chance that all these variables are highly correlated, could be correlated. And you can examine this by using a correlation analysis and by coming up with a correlation matrix, and you can check which of the two variables are highly correlated. Now, let's suppose if I have to go and build some logistic regression on top of it. Firstly, I cannot go with a logistic regression here because there are three classes. Logistic regression primarily we can use only for binary classification. Now, here I would like to tell you one thing. In the interview, people may ask like, can we use logistic regression only for binary classification? Then, see, you have to say that typically logistic regression is meant for doing only binary classification. But we can train multiple logistic regression model to deal with a multi-class classification. How you will do it? So, for example, there is a strict guidance that you have to use a logistic regression model. But here you have a multi-class. So you cannot abruptly go and say that, okay, we cannot run logistic regression at all. What you can do is, one way is you have three classes, right? What you can do is you take this one class as one of the class, like customer segment one as one of the class, and you group two and three together into another class. So you combine two and three as a separate class. So it becomes a binary classification. So in that way, you can train a model which can classify the observations into customer segment one or two plus three, right? So either it will classify any observation into customer segment one or the rest. Okay, rest means two and three. Now you train another model where you combine the segment one and three into one and put two separate. So then your model would be capable of classifying two versus all. Then you train another third model which will classify three and rest of all. So you will be building three different logistic regression model to deal with this free class problem. So we call it as a one versus all. logistic regression. Okay, so this is something, okay, you can answer in your interview. If somebody is asking like, okay, can logistic regression can be only used with for binary? If I have a multi-class classification, do you see any approach, or can we apply logistic regression in any way, to deal with that particular problem? Then you can answer, we can use one versus all kind of a logistic regression, to deal with the multi-class classification. And luckily, we have that particular algorithm available in sklearn, one versus all logistic regression, that you can directly use, and it will run multiple logistic regression model behind the scenes, where it will combine other classes into one, and it will convert the data into binary, and then it will train multiple models. Now, how it works is, let's suppose you have one single observation, right? Now, this observation will be passed through all those three models. So, first model, let's suppose it has predicted one with certain probability. For example, 80% probability. Second model has predicted, let's suppose, 2. Okay, in case it has predicted 2, again it will predict with probability. So wherever the probability is high for a particular observation, you will mark that particular observation with that particular class. So like that, you can use a logistic regression. Okay, so coming back to this particular use case, now one challenge what I see is here, these variables could be highly correlated. That kind of a problem I see. Another problem is, definitely I cannot visualize this data because I have so many input columns, right? How many I have? I have 13 input columns. But in the real world scenario, you may even get more than 50 or 60 variables also, similar to this kind of data, where you may have to face a multi-correlation problem, and even to analyze that large data, it could be difficult. Okay, and now I have to train a classification model on top of it, which can able to segment these vines into relevant customer segment categories. Now this is my data. Now what we will do is, we will apply PCA, and then we will see that with how many principal components, sorry, with how many principal components we can able to train a better model. All right. This is my Jupyter notebook. So this is the data which I have uploaded. Now here I have split the data. So before the PCA, as it is PCA, you have seen that all these eigenvectors are nothing but it will assign the weights to each of the variables, right? And we have been discussing that wherever it is all about weights, you have to scale the data, because otherwise, a variable which is on higher scale will dominate, okay, and it will get higher preference. So you better do scaling. And in the PPT, we have seen that we are subtracting mean from every value, right? But as I mentioned, you can also use standard scaler, you can use Robert scaler, you can use min-max normalizer, you can use any kind of scaling technique. So here we are doing feature scaling, where we are going with a standard scaler. Okay, so standard scaler is nothing but it will calculate the Z-score. Now I perform this scaling on train and test both, and now I'm applying the PCA here. As it is a numerical data, so I need not to do much of the transformations. If there are any categorical columns, then you have to convert that into a dummy variables. Okay, so you have to apply one hot encoding and then perform the scaling. Then you will get this kind of data. Now this is all about PCA. So I'm applying PCA here. So you will get this particular function inside a decomposition module of sklearn. So you take this particular function PCA and define how many components you want. Okay, so I'm going with two principal components for now. Okay, and I want to measure how much variance can be captured by these two principal components. So in that way, you can minimize the computation time. So let's suppose if you have 50 and if you leave this algorithm, to come up with all the principal components, then it will go and build 50 principal components. So as I mentioned, if you have n number of variables, maximum principal components you can build would be equal to n. So which would be equal to number of input features. But for our analysis, we may consider only few principal components which can explain maximum amount of variance of the data. So here I am going with only two. So this is the only parameter which you have to assign to this particular function, and just you use it and say fit. The way we do it for model training, the same way you say fit, but only thing is like if you just say fit, what it will do is it will go and calculate the eigenvalues and the eigenvectors, and that's where it will stop. If you say fit underscore transform, then it will go and apply those eigenvectors on the original data, whatever data you will pass it, and it will transform that original data into a principal components. So here I'm applying that PCA on the training data. From the training data, I'm going and calculating the eigenvalues and eigenvectors. If you observe, this particular method is exactly similar to this particular scaling technique. Here also what you're doing is you are fitting and transforming on the train, and whatever values of um, you know of mean and standard deviation for every variable, it calculates from the training data set. It will go and apply it on the test. So on the test, we are not saying fit. So fit means it will go and calculate all those parameters which would be required for transformation of the variables, and that it is calculating from the training. And it is calculating from the training and then transforming also those variables which are existing in the training data set. And the same measures it is using for transforming your test data. If you see here also is exactly the same. So it is more of a pre-processing technique, right? As I mentioned. So PCA dot fit underscore transform, it is applied on the training data set. From the training data set, it will go and calculate all those eigenvalues and eigenvectors, and then it will transform the training data set as well as the test data set. Now, how much variance has been explained, okay, by each of these principal component? That's something, okay, you can able to get by this function. This is the model PCA dot explained underscore variance underscore ratio underscore will give you the explained variance. So it says that so basically this is nothing but your percentage of variance captured by this principal component. Okay, so it is 0.37 and 0.19. So overall, these two principal components is capturing around how much? 20, almost like 56 or 57%. Okay. So now this is your training data set now after applying PCA. So I have only two columns now, and so overall explained variance is 56%. Now on this 56%, I'm going and building a logistic regression. One second. Yeah. So going with this linear model and importing this logistic regression, and this logistic regression is now giving me the multi-class classification also. Okay, so as I mentioned in sklearn, luckily this logistic regression internally will also cover one versus all. Okay, so here from the linear model, we already seen this logistic regression, how to train. Okay, so here I'm initializing that and then fitting it on the training. And after that, I'm predicting and building this confusion matrix. And look at this. Okay, on the test data, I'm getting 97% accuracy. So what it means, now you will say that only 57% of the variance has been captured, but how we are getting 97? As I said uh, yesterday, that in your raw data there could be a lot of noise. It's not something, whatever data is available, you have to consume the all the entire data, for your model training. So it seems that if even if I'm going with a 57% of variance of the data, I could able to train a model which can give me a accuracy more than 90%. So instead of going and dealing with all the variables and taking all that trouble and struggling with all the variables, it's very quick. Like, see that in within no time I can able to train the model which can give me around 97% accuracy on my test data. So, and that too only with the two variables. So this is a very quick and more effective way of dealing with large data set. Because when you're talking about large data, there could be a chance that almost more than 60% of the data could be a noise, could not be even required, for predictive modeling. So what it does is, PCA, you take entire data based on, and here another thing is like all these variables which you are seeing, probably every variable is contributing a very minimal to the overall information. Okay, so it's something like if you just take alcohol, probably based on this alcohol color intensity or some magnesium content or malic acid content could be defined. If the alcohol content is high, possibly the acid could be high, color intensity could be high, uh, magnesium could be high, right? So we don't even require all those columns when we are considering alcohol, right? But if you have to do it manually, it's going to take a lot of time because you have to go and construct that correlation matrix, and then you have to check which of the two variables are highly correlated and which one to drop. So all that thing you have to do it manually. So PCA is a one good technique where you just pass the entire data and it will take care of rest of the things, right? It will create the principal components, and every principal component would be independent in nature. Okay, so as they are orthogonally placed in the n-dimensional space, so the correlation between the principal components would be very, very low. So you can consider those principal components for your model training. And in this logistic regression, you remember one strong assumption is that my all input variables are independent. So that would be fulfilled if you are going with this PCA. So here with this PCA, I'm going with only two principal components, which can cover 57% of the variance. And with that 50% variance, when I'm going and training the model, I got the accuracy of around 97% on my test data. And you can even check it on your training data set and see that how much accuracy you're getting on the training data set. So here, what further iteration you can do? So you can just change the number of components to three, and then you go and perform. Okay, so let's do it. Okay, let's run this. Meanwhile, if anybody is having any question, then do let me know. Okay, so I'm changing it to three, and let's see that how much three top principal components would cover the variance. So the last one, the third one is covering only 10% of the variance. So let me take 10 now. Okay, 10 principal components. Let's print it. Okay, 10 is not possible. What it's saying. Must be between 0 and minimum n samples and features. Okay, features, why it is not coming. Strong. Okay, sorry. The training data set has been transformed, right? So that's the reason it is not coming. Okay, now it will work. We have only three features here. That's the reason it is not working. Let me go and load the data again. Hopefully it should work. Yes, it worked. So what was happening is so here the training data set is getting changed, right? I'm applying the principal components on top of it. So earlier where I've used n components equal to 3, so my training data set has only 3 features. So that's the reason it was not taking 6. If you see here, the first principal component was able to capture 37% of the variance. Gradually, it goes down. The second one is capturing 19. The third one is capturing 10, then 7, then 6, and then 4. Okay, so gradually, the amount of variance captured by these principal components will gradually decrease. So the top few principal components can able to cover maximum amount of variance. So if I go and say, so now 85% or 86% of the variance is being captured by these 6 principal components. Now we will go and train this model. Now it may lead to overfitting. Let's go and check. See, it is giving me 100% accuracy. So that's something you have to go and cross validate it. You have to check on training, you have to check on test, and then accordingly you have to choose appropriate number of principal components. It is like principal component is just a pre-processing step. Once you get principal components, just consider that as normal features. Okay, the way we have seen in earlier use cases, how we have trained the model, you have to train the model just like that, and all the validation and evaluation of that model, you can do it the way we were doing earlier. Okay, in other use cases. Nothing else would change. The only this part you are adding it to entire solution where you are transforming your um, actual features into some other form, which are these principal components. Rest all the steps are same for training the model. So any questions, guys? Is it clear? Any questions on this? So with this, guys, we are done with unsupervised learning. So anybody has any questions on the unsupervised learning? Did you guys get clearly what is the difference between supervised and unsupervised? And did you get the differences between all the different algorithms what we have discussed so far?
Largely it is clear. Shrikant, yesterday, the same page that where we discussed now, lambda plus two, that below the lower section, you did not discuss that unit eigen vector and all, something like that is there. Same slide.
Okay, so that is little confusing on the slide. So that's the reason I shared you the Word document. So in the
Okay,
Word document, if you go, those are the same steps, but it's like in the slide, I cannot accommodate every step, right? So I skipped couple of steps. So so that's the reason I didn't walk you through in through that particular slide step by step. So that's the
okay,
reason
okay.
I created this Word document with a proper explanation. Go through it. Okay, I don't want to spend a lot of time on that particular calculation. Go through that Word document. If you have any questions on any step, then do let me know. Okay, we will discuss.
Sure, sure, sure. Thanks.
Okay. So, what shall we discuss now? Okay. So I thought of, moving to a deep learning today. But before that, do you want to discuss anything, guys? Because it is a very logical stop now. Because we have covered statistics, we covered supervised learning, we covered unsupervised learning. Anybody has any question on any point? Let's have a, let's clear it out now before jumping into deep learning. So firstly, guys, are you practicing? Are you spending enough time every day on this or not? I doubt, because you guys are not asking any questions, or rather, we are not discussing. So it's very hard for me, to uh, accept that you are getting everything. So I leave it up to you guys. If you are okay, then it's fine. We will move to other topic. But if you have any questions, or see, don't hesitate. It's okay. Okay. When I gone through all this learning phase, I can understand. If you have, and don't keep that small doubt also in your mind, because that small doubt will not allow you to move forward. Okay. You will get stuck at one point. So if you guys are having any minute doubts or any questions, please clarify there and there then itself. Otherwise, it's going to stop you, to understand further topics better. Like, so if you have anything, just we can discuss, or else I'll quickly move to a deep learning topic. Okay, so all right, so get into it. Okay. Now, when we are talking about deep learning, okay, it's all about neural networks, guys. Okay, so neural network is a very, very big, I would say, invention, okay, which has happened in this data science space, which has kind of changed the entire picture about, of this model development. So, how the things changed was, see, you have seen till PCA, what we have done is that was one of the technique to address the larger data problem, okay, or the curse of dimensionality can be solved to some extent with PCA. But still, in the real scenario, okay, the data was growing to a larger sizes, okay, and even the PCA failed to um, you know, bring out some efficiency or effectiveness in the whole model development cycle. So then people thought, why can't we come up with some better algorithm which can be scaled? Okay, which can go and mine deep insights from a larger data sets. Okay, and that's where this neural networks came into picture. So what these guys have done is, when see in PCA we have seen that if there could be some noise, then with few principal components you can able to achieve your desired results. But what if all the 50, 60 variables which is there in the data set all are relevant, and let's suppose all are independent variables, and every variable is giving some good information about the output variable. So generally, typically it happens when we are talking about any complex problem. A complex problem is something where to decide your target variable, you may have to look into multiple dimensions. Okay. So, for example, document classification. So, for classifying a document to any one category, you may have to look into lot of keywords in that particular documents. Okay. If I want to, for example, there are various policy documents, and I am looking out for one specific policy documents uh, related to appraisal, let's suppose. So there would be a lot of HR documents and policy documents where there could be a lot of common words. So they could I would be looking out for, or the model rather, would be looking out for some specific keywords which would be present only in appraisal-based policy documents. Okay, so in that case, I may have to deal with all the common words as well as the specific words. So here, just imagine how many keywords I may have to uh, examine to classify that particular document into a specific category. Now, this is something if I'm expecting from a algorithm, then whatever algorithms we have discussed, those algorithms might fail because the way they work, it is not meant for such a big high dimensional data. So that's where these neural networks has been discovered, and this neural networks is being what do you say? They have been. I'm not finding out the right word. Basically, it is the outcome of our human brain. Okay, the way our human brain functions. So they have come up with the same mechanism and they have constructed this neural network. And we will see that what kind of similarity you will find between this neural network algorithm and our human brains. So it is and this ANN is not something which has been discovered of late, okay, in recent years. It also discovered in 1960s or 70s, okay. But at that time, it was just on books. It was just a research paper at that time. People just thought something like this could be useful when there is large data and when we are dealing with high dimensional data. But at that time, we didn't have that much compute power. We didn't have those kind of machines, where we can run and test. And even at that time, they didn't have that much large scale data available. So, it took time for them, to test it. And once they tested it, they found that this is much more effective and efficient when it compared to all other traditional machine learning algorithms. And that's how, it got adapted. And from there, the word AI also uh, in AI, this artificial neural network has become a very key algorithm because it is it is directly mimicking the human brain. And artificial intelligence is all about intelligence which is man-made, where we are making the machines more intelligent. And if those machines are using this artificial neural network, now it becomes even much more closer to humans because this whole algorithm works in a very similar way as our human brains. So now, by sitting in front of your system or in front of your mobile, lot of different inputs might be entering into your brain, right? So whatever is happening in front of you, you are perceiving all that information. Something already might be there in your brain, something you might be planning, for the day. All that information is kind of running in your brain. So these are all our input signals. I'm talking, that is also going, whatever you are seeing, that is also feeding into your brain. Okay, whatever sounds and whatever people are talking around you, that is also getting into your brain, right? So our brain is the way it uh, has been made is that our brain can take multiple information. Firstly, we have these five senses, right? So all the time, these five senses will start giving you the signals. If you touch anything hot or if anything pricks you, immediately, you react. So we have that sense organs by vision, by smell, by touch, and all those. Our brain is continuously taking all that signal, and then it is processing it, and based on that we take action. So now this is the typical how the brain functions. And in the brain, it's a very complicated machine. In our human body, if brain doesn't function well, so entire body will fail. Okay, you cannot even stand and move and do anything. So everything depends on your brain. So that's the reason people say that, okay, you have to keep your brain calm and healthy so that you can lead a very healthy life. If your brain doesn't function well, okay, rest, entire body will not function. Okay, so healthy mind, healthy body, we say, right? So that's very true. So what is this artificial neural network? It is a neural network which usually a computational network based on biological neural networks that construct the structure of the human brain. Similar to the human brain, as neurons interconnected to each other, artificial neural networks also have neurons that are linked to each other in various layers of the networks. Now let's go and see that how are what is the similarity. So basically, I am a biological student. So in my 12th, I had biology as well as maths. So I also prepared for medicine for an year, and then finally, eventually, I moved into engineering. Uh, so I have the complete understanding of this human brains. So in human brains, you need not to go and read about human brains. But the way our human brains are made is that we will have billions of neurons internally. Those neurons are the very granular, um, what do you say, component of our human brains. And you will be amazed that we use a very limited percentage of our brain neurons. And for that, there was an experiment conducted on the Einstein brain. So, Einstein, we know, is one of the most genius and intelligent person we had. So, these scientists, they took his brain and then they examined, how this guy could be so genius. And they found that in his brain there were more than 90% of the neurons, I guess, or 70%. I'm not sure with the number. Was active, while in a typical normal humans, only 10% or less than 10% neurons will be active. So that was the difference between his brain and the normal person's brain. So what are these neurons? There are 80 million neurons, I guess, or billions. Okay, that will be there in the human brains, which will make that brain so powerful. And now in each of the neuron, this is how its structure looks like. So we will have the dendrite. Dendrite is something, okay, which will connect one neuron to another neuron. Okay, and that's where the transmission of the signals would happen. So the previous what do you call this neuron will pass some signal to the adjacent neuron. So whatever dendrites you are seeing, right? So that many neurons will be connected to each of these particular neurons. Okay, so here the signal will come. Signal will be received from the dendrites. So it is a nucleus. Every cell will have a nucleus where some processing will happen, and then the signal will pass, and it will again pass through axon, and then it will transmit it to other neuron through synapse. So where the exchange of the information happens, that is known as synapse, where it will be transmitted to other neuron. And other neuron will again have dendrite, which is the receiving uh, part of the neuron. And then again it will receive, and then again it will be processed and moved through axon, and it will be transmitted to the another neuron. So here, every neuron is different, and that's how our brain can perceive various signals, and it can process it on the real time. So here it's not one single neuron which has to do our entire job. So here there would be multiple neurons which will think from multiple direction, process different signals, and then that's how it will we can think multiple things at a time. So similar to this structure, okay, we have this artificial neural network structure. It is a three-layered structure typically. One is like input layer. This we call as a hidden layer, okay, where the processing will happen, and this is the output layer. So you can consider this output layer as synapse, this hidden layer as this axon and nucleus, and this input layer as the dendrite. So that's the similarity. Now, this ANN can be as simple as having only one single node in the hidden layer where the entire processing is happening. Okay, it will consider all the input signals, and this only one single node will process. And it could be as complex as having multiple hidden layers with multiple hidden nodes. And every hidden node will take the input signal and it will process some different information, or it will come up with some different output altogether. Okay. So now this is entire neural networks. When we are scaling it to multiple layers or multiple hidden nodes, is called as deep learning. Because what we are doing, we are trying to extract all the different information, different kind of information from different dimensions, and then we are passing it to layer by layer and processing it, and then finally we are trying to achieve or trying to do the prediction, okay, which is closer to the actuals. And this whole thing happens in a supervised way where we are passing the actual values and allowing this network to tune itself so that the prediction which is coming out from this network would get closer to the actual values. Now, how all this thing happens? Okay, so that's we have discussed. Okay, so this could be as complex as this. Okay, so this is my input, these are the hidden layers, and this is my output layer. So just see all these lines. How the and these lines are nothing but these are the information. Okay, this is the data which is getting passed and getting processed in every node. So if you see this particular node, all the input is getting passed to this node, and again, all the inputs are getting passed to this particular node as well, and this particular node as well. So every node will act differently and it will try to come up with some different information. And it will try to find some different, what do you say, details, or it will try to mine different insights from the data. Okay. So, as in our human brains, every neuron will function differently and it will try to extract some different insights from the input. The same way here in this ANN, every hidden node is built in such a way that the same function, the same processing will not happen in all the hidden nodes. Every hidden node will try to find out some different insights from the data. And that's how the hidden insights can be derived from the data by using this ANN technique. And that's the reason it has been named as a deep learning, because it can go deep inside the data and can mine some hidden insights from the data. So typically it is ANN is a three-layered structure. One is input layer. Input layer will be always one layered. Then we have the hidden layer. This hidden layer can be multiple. Okay. We can add as many number of hidden layers. But again, if we keep on adding more number of hidden layers, then again my whole network may prone to overfitting, because it will learn too much from the training data set and it will improve the overall accuracy, but but that whole network may fail. Network means the model may fail on the test data, because it will learn too much and it will try to find out such minute insights from the data which is present in training data set but probably may not present in the test. Okay, so again you have to make sure that how many hidden layers would be optimal for training the model. So these are the definitions. Input layer, it accepts input in several different formats provided by the developer or the programmer. Hidden layer is present in between the input and the output layer. It performs all the calculations and find hidden features and patterns. So this is something you have to remember. The output layer, it goes through a series of transformation using the hidden layer, which finally results in output that is conveyed using this layer. Okay, so now I'll give you a scenario. For example, what shall we take? Okay, so let's suppose I have to classify a particular image as car or a bus. Let's suppose I'm training this network to classify an image as car or bus. So it's a binary kind of a classification. So here the inputs what kind of input you will pass. So you will have an image, first of all, okay? You will have an image of a car or a bus. And from that particular image, you have to extract some features. So firstly, it could be, let's suppose, shape, color, size, or something else, some other features, okay? What it could be, shape, color, size, uh, something like edge. We can say edges. Okay, how many edges are there? Let's suppose these are my four inputs. So now this particular would thing may give higher weightage to shape. So this is the information, and here the weights would be defined. Now this particular node may give high weightage to shape, and it will learn like, okay, if the shape is something like this, then what is in the data, how many times it has been classified as car or a bus. Now this may, and it will also take another features also, but the weights probably could be less when compared to shape. Now this particular hidden node may give more weightage to size or edges. Okay, then this particular node may give more weightage to other features. Now, based on that, definitely it will have some kind of output. Okay, it will come out with an output, and that output again you can pass it to a separate layer. Now, that information which is coming out from this particular node will be passed to the other node, and the other node will again will give assign the weights, different weights to different features. So this node may give more weightage to this particular feature, or this may give more weightage to this may give more weightage to both the features, and this may give the average weights to all the features, something like that. Okay, and then finally it will help uh, in this particular output layer to decide whether that features which are coming out from the image is for a car or a bus, and that it will give it by a with a probability. So that's how this network would work. But how this whole processing is happening in this each of the hidden layers. So there are some known as transfer functions, transfer functions and activation functions. Again, the mathematics would be super complex, okay, but at a high level you need to understand how these functions would work, right? So basically, here if you see the hidden nodes, when it takes the data from the previous layer or from the input layer, it will define the weights to each of the input features, and this is how the linear equation it will create. So if I have four variables, then it will assign the weights to these four variables as W1, W3, W2, W3, and W4. Okay, and it will also add some kind of a bias. Okay, bias is what it is. It is a kind of a constant which will try to balance the equation. We have seen in the linear regression, we have seen in the logistic regression, there is a constant term, right? So it is just like that. So this transfer function, it will take the input data, and then it will assign the weights to these input features, and this will happen in every node. Okay, now then we have the activation function. Now here through this particular transfer function, the information will be passed from this previous layer or from the input layer to this hidden node, and again here there would be a transfer function. Here there would be a transfer function. So the sigma, I'm putting it as a transfer function. So where the weights will be assigned, so I'll put it here. So here it is like sigma, okay? So where it is taking all the input features, and then it is coming up with the weights, and also it will also add a bias. So this something is a bias term or a constant term. So with every network, there would be some kind of a bias term. It will be added. It's not compulsory, but if it has to balance, then it will add constant. Otherwise, it will be there wouldn't be any kind of a bias term, and it will be done automatically the way the program works. After that, now see the weights are being calculated, but after that, some processing also needs to be done in the hidden nodes. Okay. And that is done by this activation function. So there are several activation functions, but these are the four important activation functions. So one is tanh. Okay, tan it comes from trigonometry, right? So what it does is whatever values you are getting through this transfer function. So transfer function is nothing but a linear equation where it will take all the input features and it will put that into this particular equation and you will get some value, right? You will get some value. Is that value is directly passed to the subsequent layer? No. On that particular value, again, some transformations will be done. And that transformation is done through this activation functions. What are those activation functions? We have tanh, we have ReLU, we have sigmoid, and we have linear. To have that slide, just a second. I had one slide which can. Hmm. Yeah, here it is. Okay, so how it works? So tanh. So this is the formula of tanh. Okay, so tanh is the function which will transform that value which is coming out from the transfer function to some other form. So z is that value. So that z value will be substituted in this particular equation, and whatever value is coming out of this particular function, now that will be passed to the subsequent layer. So why all this thing is being done? So see, passing any value between minus infinity to plus infinity will again make the things too complicated, right? In terms of processing. So what these activation function will do is it will define the range. So just like in sigmoid, whatever value you pass it to the logic function, it will give you the output between uh, 0 and 1, right? Now this particular tanh function, whatever value you pass it to this particular function, now that values would range between -1 to +1. Okay, so that's the beauty of this particular function. Now then we have ReLU. Whatever value you pass it to this ReLU function, just see this is the only function. It will take the max. If the value is positive, then it will take as is. If the value is less than 0, then it will make it as 0. So if you see here, this is my x and this is my y output of this function. If I'm passing any value which is greater than 0 to this particular function, it will take as is. Okay. So it is 2.5, then here it is also 2.5. Here it is 5, then this would be also 5. Okay, but any value which is less than 0, it will be equal to 0 only. And you will be surprised that ReLU is the most popular and most, I would say, um, best activation function, among all the activation functions. Now we will use ReLU in computer vision problems also most of the time. We also use it for text-based problems. So ReLU is much more effective when compared to any other activation function when we are considering the hidden nodes primarily in the hidden layer. Okay, there we go with this ReLU most of the time. Now, all these activation function is something which you can try with. Okay, so whatever different kind of transformations you want to try, you can just change this activation functions, and then you can see what kind of results you are getting. So these activation function is one of the hyperparameters which you can fine tune, to improve the accuracy of this particular network. Okay. Now for the sigmoid, this is my loss function. And majorly sigmoid is used in the output layer, because in the output layer we need the probability values. So the output should be the probability values. That would make sense. If I put ReLU in the output layer, so whatever value coming out of the ReLU function, I cannot able to understand that, because it is taking some data and then just uh, it was converting all the values to positive values. Basically, it is considering the positive values only and discarding all the negative values. So ReLU, I cannot use it in the output layer. ReLU, I can only use in the hidden layers. Okay, so but sigmoid, we have seen that, okay, sigmoid kind of a transformation we have done in logistic regression, and that is giving us a good probability values. So if you want the probability values as the output, then you can use this sigmoid function in your output variable, in your output layer. Then we have step function. What this step function will do is it will range between 0 and 1. Okay, so it will just take not between, it will just take two values, either 0 or 1. Okay, so if the values is greater than 0.5, okay, it will mark it as 1. If it is less than 0.5, it is mark it as 0. Okay, so step function is another such kind of activation function. So this is some of the examples. So every function will have a separate kind of every activation function will have a separate function which it will use to transform the values to some other form. So tan H equation we have seen, ReLU is all about max, sigmoid we seen, and the linear is just as a transfer function. Whatever data comes from the transfer function, it will pass it as is. So no transformation will happen. So this is a linear function. So linear function as a transfer function itself is building this linear equation. So when you are using this linear function, it will pass it as is. Now this linear function, we can also use it in the output layer, and it will work just like linear regression. So it will take all the input. um so for example, in this layer, if it is like only one single node, I will use this particular adder. So let's suppose this is my output, and here I have defined it as linear. Basically, we will use linear when we are dealing with a regression problem where we have to predict some numerical variable. So here it is only one single, so it will work just like a simple linear regression. And the way simple linear regression comes up with a linear equation of a straight line, the same kind of an equation will be built here in this output layer, and we will get the output. Now, if it is a multiple nodes here, then it will work as a multiple linear regression. So whatever output is coming out from the last hidden layer, it will process in the output layer just like a linear regression, and it will give you the output. So before this last hidden layer, you can add as many hidden layers, which will kind of try to refine the information at every layer by layer and by layer, so that this the linear function in the output layer can able to get all the meaningful insights from the data, which would be useful for that particular linear regression algorithm to come up with a better output. Okay, so you can consider these hidden nodes, hidden layer, as data processing or insight extraction layers. Okay, it will try to extract information in much more meaningful form, layer after layer, and then it will pass it to the output layer. So, as I said, these are not limited. you have leaky ReLU as one of the function, and you have step function. You have many more activation functions. All that list of functions I will show you. But these are the most broadly used activation functions. So typically the TANH and ReLU, these are used predominantly in the hidden layers. Okay, and these sigmoid and the linear, these activation functions are typically used in output layer. If it is a regression problem, we go with a linear. And sigmoid generally we use it only for binary classification. So if only two classes, then only you can use sigmoid in your output layer. Otherwise, there is another activation function known as cross entropy. Okay, so that activation function we will use for a multi-class classification problem. So we will talk more about those activation functions when we deal with the use case. So I hope you understood by now how this ANN works. So it will, whatever input is passed from the input layer, it will come up with some linear equation and it will assign the weights, and that is done through this transfer function. And whatever output is coming out from the transfer function, that will become the input to your activation function, and those activation functions you have to define in this particular node how to transform that data. So if we take ReLU, then whatever output coming out from the transfer functions, it will check whether it is positive or negative. It is positive, it will keep it, pass it as is, otherwise it will make it as zero. Okay, and that information will pass it to the, and that would be the output for this particular hidden node. Now again, in the subsequent layer, again, every hidden node will function exactly the same way how this hidden node, for this particular hidden node, a hidden layer, or this hidden node, this hidden layer will become the input layer now. Okay, now it will take and it will assign the weights. The transfer function will come up with the weights, and then output of the transfer function will be passed to the activation function, and whatever output will come, that will become the input to this particular output layer. Now, in this output layer, you can define the whatever, if it's a binary classification, define it as sigmoid, or if it is a linear regression problem, then you can define it as linear, or if it is multi-class classification, then you can put it as cross entropy or softmax. So we call it as softmax. Okay, so this is how it works. Now just compare this particular neural networks with our traditional machine learning algorithm. So in machine learning algorithm, typically we were using, if you see that this particular output layer is kind of taking only the raw inputs. So in the linear regression, what we are doing, we are just passing the raw inputs to the algorithm, and then the linear regression is giving us the equation. Okay, so that was as simple as that. But here we are in between, we are adding too many layers here. So what it is doing, it is refining the information layer by layer, layer by layer. Okay, and then the refined features are now getting passed uh, to the output layer, where that particular refined information is getting transformed into a meaningful insights, which we can use it as a predictions. Okay. So now your question could be how the learning is happening. It's not like at the first go it will come up with the appropriate weights. So now how these weights are getting calculated or being identified. So at the first run, all these weights are randomly assigned, will be randomly assigned to these hidden nodes. So it will pick up like for this particular hidden node, let's suppose it will pick 1.09. For this particular input feature, it will pick up as 26. So it will randomly assign the weights for at every layer. Now, once it is randomly will assign, so this is the softmax which I was talking about. It converts a set of numbers into probability used for classification for multiple variables. Okay. Now, these weights, which is being assigned to from this input, will be assigned randomly. And that's how this transfer function will be defined. And that transfer function output will be passed to the activation function, and then appropriate values will be passed to the subsequent layer. Now, this is important thing which you need to understand to know that how this neural network is getting trained and how it is learning. Now, first, the initial weights will be assigned, and based on those initial weights, the output will be generated at the output layer. Now, let's suppose randomly assigned, and some output will come, and definitely that output would not be accurate because no learning has happened. It is just randomly the weights have been assigned, and we are calculating the output. But that is the starting point. That's how from that point it will start improving the results. So once the output is coming out from the output layer, now all these output values will be compared with the actual values, because we are passing the label data. We are passing data in which there is a output column also. So it is a supervised learning technique. So here I'm passing the training data set in which I also have the output variable. It will consider all the input variable, and with the random weights, it will go and first calculate the output, and that output will be compared with the actuals. And the errors will be calculated. So here also it's all about cost function. Okay. So when you talk about linear regression, the cost function could be, what is the cost function we discussed in the linear regression, guys? Mean squared error, right? So that would be my cost function. If it is uh, classification, then I can go with accuracy. And if it is like multi-class classification, I can define some other cost function like cross entropy or something. Entropy, you know about it, right? So I can define that cost function. And there is, again, in this Python function, you, you will get one argument where you can pass these cost functions. So the cost function will be calculated. So at the first run, let's suppose that mean squared error or accuracy is, so I will take 1 minus accuracy. I'll calculate the errors, right? So error is something around 70%. Okay. So it will see that in which all observations the error is there, right? And that error signal will be passed from the output layer back to the input layer, till input layer. Okay. So the error signals will pass from the output layer back to the input layer. And what will happen? These weights will get optimized. The first time it will randomly assign the weights, and now from there the tuning is happening, right? So learning is happening. So if there is a 70%, now it will come back and it will change the weights, and then again it will be processed from left to right, and again the output will be calculated, and the cost function will be calculated accordingly. Now let's suppose in the second run it has your error has reduced to 65%. So again, there could be the scope. Again, it will go back. Again, update the weights, and then again calculate the output. And based on that, again, the cost function will be calculated. Now, this one cycle from left to right and right to left is known as epoch. Okay, and this left to right process is known as feed forward process. So here the input is getting feeded, okay, in the forward direction. So feed forward process, or we call as FFP in short. Okay. And from the output layer to the input layer, when the information is passing, that is known as back propagation process, which we call as BPP. Okay. And the one feed forward and one back propagation process is considered as one cycle, which is we call as epoch. Okay. Now, can you remember now when we talk about cost function, when we talk about updating the weights, you can easily recall algorithm which we have discussed initially, which is known as gradient descent, right? In whatever use scenarios we discussed about gradient descent, the main objective of that gradient descent was to optimize the weights so that it can uh, the cost function gets minimized, right? So how it will come up with the optimal weights? It will find out the point at which the cost function is the minimum, right? So that is known as global minimum point. It will go and search for that global minimum point at which the cost function is the minimum, and those will be the optimal weights. The same thing here also we will use the gradient descent, and the gradient descent is the very powerful algorithm, optimization algorithm, which is being leveraged in most of the algorithms. And you have seen, right? So we have talked about gradient descent multiple times, right? So the gradient descent is one of the powerful algorithm which is running uh, uh, in multiple algorithms. Okay. So this is how it works. It will randomly, the neural networks will start at one point. Okay. And every time it will go and optimize the weights so that it reaches to this minimal point, and that is known as global minimum point, right? Uh, this is a screenshot what I have taken from Andrew Nick course, which you can find it in Coursera. If you want to understand more about mathematics, so there is a, good ML course, on Coursera by this Andrew NG. So we called as Andrew Nig, and he's a very famous in the data scientist community. So people follow him like crazy. Even you will find a lot of video about him, on YouTube. Now he's the guy who is one of the co-founder of this Coursera. So you can go and watch his video, and he has very nicely, if you want to understand the mathematics, and in that particular course also that mathematics part is optional. So if you want to understand the mathematics, how these derivatives are getting calculated, how these weights are getting optimized, then you can refer to this particular course. So basically, if you see that every time, uh, this this cost function, which is my JW cost function at this particular weight, it will get there would be a partial derivative which will be done on that particular cost function with respect to a particular weight. Okay, particular coefficients you can say. And there would be some constant term which will get multiplied to this partial derivative. And then that whole term will get subtracted from the original weights. And that's how, the weights will get optimized every time. And the same thing will be repeated. So this is a repeat function, right? So this will be repeated till it reaches to this particular point where this partial derivative would be equal to 0. So that would be my minimal point. So now this alpha, what you're talking about, this is known as learning rate. Okay. So what is this learning rate? It defines how big and how small step your algorithm can take, to optimize the weights. So if you see here, if I increase this alpha here, okay, definitely this particular value would increase. And then what you are doing is from the original weight, you are subtracting a big value. So that means it is going to shift with a bigger value. So for example, in this case, if the alpha is high, then the shift from this particular initial weight to the new weights would be larger, right? If the alpha is low, if it is minimum, then it will take a very small step. This also we have discussed, right? what is the problem if we increase the learning rate and what is the problem if we decrease the learning. If we increase the learning rate, then this particular algorithm may miss out the minimal point. So for example, if it is here and I'm taking a higher, bigger alpha value, it may jump from this particular point to this particular point, and it may miss out this minimum point. And again, it may jump here, again, it may jump here, again, it may jump here. So it will keep jumping from one point to another point, but it may not land up to the exact minimum point if we are taking a larger learning step. But one advantage with the larger learning step is, let's suppose the algorithm, my ANN starts here with a random weights. Within 2 to 3 steps, it may come closer to it will not reach to the exact point, but it may come closer to the minimum point. But if I'm taking a smaller alpha value, then just imagine how many epochs it has to run, to reach to this minimum point. What is epoch? Epoch is one cycle at which the weights are getting updated, right? So at every step, the weights will get updated, and to converge and to reach to the minimal point, it may take longer time when if I'm going with a small alpha value. So what is the best way? You have to consider this alpha value or the learning rate value neither too large or neither too small. Okay, not too small. So larger learning rate, it may overshoot and it may skip the minimum point. Smaller learning rate, many iterations until it get converged, and sometimes it get trapped in the local minima. That is another major disadvantage of the smaller learning rate. So small, 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 small. It when it reaches here the slope is equal to 0, then it will stop here. It will not further move. If we have little bit larger learning rates, so there could be a possibility that it may jump here. It may skip this trap. Okay, and further it may jump here, and then again it may further go here and it may reach here. Okay, so here in this smaller learning rate, this is the problem. Okay, though it can reach to the global minima, but sometimes it may get into this local minima trap. And we have also discussed like how this local minima trap can be avoided, right? How this local minima trap can be avoided if we go with a batch gradient descent or a stochastic gradient descent. Batch gradient descent means a different batch of data will start from different points, uh, and based on the outcome of each of the batches, we can decide which one is giving us the minimal cost function, and accordingly we will consider those weights. Stochastic is more about it randomly. The entire data will multiple times it will randomly iterate from different points. Okay, so that the global minima is not missed, right? Those are the two approaches. Uh, the time. Okay, so I'll stop it here. Uh, but here, if you see this neural networks is pretty complicated. Okay, it comes under the complex algorithms. So we have to be very careful while adding the hidden layers, and while using this neural networks, we have to test it multiple times to make sure that this is not overfitted model. And we know that if we are going with a complex algorithms, the variance in the model may increase, and because of that variance, the error may also increase, right? So we have to have a proper balance between the bias and the variance, and this is very very important topic, and I'm iterating it multiple times. Yesterday also I talked about this. So you have to choose the algorithm which is low on bias and low on variance. So you have to take that particular trade-off. If there is a high bias, again, it is a problem. If there is a high variance, again, it is a problem, and that may lead to an error. So model training is one aspect, but testing and making sure that that model is a robust is a very critical step in the whole model development. You can come up with a model, so that's not a problem. Okay, but deciding which model to take into the production, which is more reliable, more robust, less prone to bias, less prone to variance. That something is very important. And we have seen how you can confirm that. You can use cross validation technique. You can deploy it in a very, I would say, in a very isolated environment, in a testing environment first, and then test it for some time. And if it continuously, consistently, if it is giving a better result, then only you move it to deployment. So there is a various deployment strategies which you can use. So there is a canary deployment. Canary deployment is like you slowly you deploy. Okay, so let's suppose the status quo is happening. People are 100 people are using some technique, to make the decision. Do not abruptly change that particular strategy of decision making to this model based decision making process. What you can do is slowly, gradually you change it. First, you give it to 10 people, say that, okay, use it and see that, okay, how is it working? Now they will give the feedback. If it is working fine, then give it to 20, then give it to 30. That's how, you move majority of your users onto your model, you know, slowly, one after the another. So that is known as canary deployment. Another deployment is known as blue-green deployment, where you can just retire the previous process and then move this new model there. Okay, that is known as blue-green deployment. So you have to see that which deployment strategy would work in your use case and how you should evaluate, because that is the core thing. Okay, it's not simply just go and train the model and just test it once and then give it to the business for making the decisions, right? Because you are seeing in every use case, you have seen that how critical that model is in terms of predictions, right? If you are saying that particular person will churn, just imagine, okay, how much business would put their efforts to retain that particular customer. If it is, if that person is not going to churn, but your model is predicted that is going to churn, let's imagine that customer will get annoyed if it is getting too many calls, or he will get overwhelmed by looking at the number of emails and everything. That is also not good, right? So that's the reason evaluation and testing is very, very important before deploying that particular model. So now you might be thinking that this ANN is so good that it can process, it can mine, but we just not directly go with ANN. We go with the simpler models first, and if the data is complex, if and you have seen that with the PCA we solved that problem, right? And it has given me the 95%. If that is done, then why we need to go with ANN? Because first of all, it is a complete black box model. You cannot able to explain ANN because just see that how much level of processing and transformation is happening. Okay, if you are going with the three hidden layers, and in each of the hidden layers, let's suppose if you're taking four hidden nodes, just imagine how much pre-processing is happening. So you are just losing all your um, uh, you know information in the original scale, right? So all the information is getting processed, refined, and it will be passed to the output layer in altogether in a different shape, okay, and in a different scale. So it cannot be interpreted, it cannot be explained. But however, if the data is complex, it can able to give you a better results. So again, you have to check, do we really need ANN for your scenario? Even though if it is not explainable, that kind of a decision you have to make along with your business, and then you go ahead and train that particular model. Okay. Now we will see how we can use ANN on the structured data, and then after that we will go further into other different kinds of neural networks. So we have convoluted neural networks, which we will use it for image processing and for computer vision. And then we will also talk about LSTM, which is long short-term memory. Uh, um, Again, those are one different kinds of networks, neural networks that will generally be used it for text data or for time series data. So that also something we are going to discuss. So these are the uh, three algorithms which we'll cover in the deep learning. because these are the most powerful and most popular algorithms when we talk about deep learning, but there are many more. Now, when we are talking about generative AI, these are the extended or different kinds of neural networks, which we call as transformers. So those transformers are generally used for generative purpose. Okay, so one last thing before closing this. See, this neural networks, which we have discussed. Now, these hidden nodes are called as even perceptrons. You may come across with this word perceptrons. Single perceptron neural network generally does not come under deep learning because you are using only one single perceptron. It is just like you're passing one input to this particular single node. Here, the all processing is happening, and then it is getting passed to the output. It's a simple processing. So typically, single perceptron neural networks generally you will find in any resources or material, they will also include that into machine learning. So don't come back and say that, okay, you said that ANN is a deep learning algorithm then, but in the machine learning, it is showing, okay, as a single perceptron neural network. So when they're talking about single perceptron neural network, that means they are talking about one single perceptron, one single node. And again, machine learning and deep learning are not two different things. Deep learning is a subset of machine learning, guys. So deep learning is a subset of machine learning. So do not consider it as altogether a different topic. So there is a overlap, and that overlap is this. Neural network with a single perceptron comes under machine learning. When it is extended to multiple layer, then it comes, completely into deep learning. Okay. So we will talk about a use case on Monday, and then we will get into convolutional neural networks and LSTMs. Okay, and after that, I will explain the concepts, and after that, Vikrant will take over the classes and he will show you the use cases, and then he will explain you the Spark. We will get into Spark. Okay, and once the Spark is completed, then again I will take the classes and we will talk on Tableau. Okay. So that's what I have for today. So guys, if you're not on track, then I would request you to go and start revising all the topics. Do not keep it pending because it's going to be difficult later, to cover all those points. Okay, so what we can do is I will take one class sometime when I'm done with this deep learning topics, and I will give you a again quick recap of all the algorithms, whatever we have discussed so far. If you want that, do you want that a quick recap? Is it required, or you're good?
Yes, sir. Very
Okay, so we will give you a quick recap. We'll do a quick revision, and at that point, if you have any questions, then feel free to ask and get it clarified, and then we will comfortably, you guys can move to Spark. Okay, and on Spark, we will see that how the data processing can happen, all the things, whatever we have done in Python, we'll see that how that can be done on Spark. And this Python understanding would definitely help you when you are using PySpark, because in PySpark's only few syntaxes may change, but rest of the things would be just like Python. Okay, so if you guys are not comfortable on Python, I would rather suggest you to practice till you, because then only you will able to get quickly whatever Vikrant will cover in Spark. Otherwise, that part will be also would be hard for you to understand, and everything will get confused, and you will get confused. Everything will get mixed up. Will not be clear that whether it is a pure Python syntax or whether it is a Spark syntax. So to avoid that, I would say please practice Python, get a good understanding on Python before uh, PySpark classes starts. All right, then that's all from my end for today. Let's connect on